So what are we talking about? We are again talking about interacting systems. We have a complicated n-body potential, which means it's a function of R1, R2, all the n vectors for n atoms. And in order to describe the system, we really need to look at joint probabilities. For example, the joint probability of finding two particles, a particle 1 at R1, particle 1 at R2. We talked about this. This is going to be proportional to integrating out dr3, dr4, dot, 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 e to the power minus beta u of Rn. Then we talked about rho 2 of R1, R2, which is going to be larger than P2 of R1, R2, because this is the probability of finding any two particles at R1 and R2. So this is rho 2. And then we said that for isotropic fluids, rho 1 of R is going to be rho, radially symmetric isotropic fluid, even if there are interactions. And rho 2 of R1, R2 is going to be rho square if there are no interactions, right? These are the type of things we derived. And what else? We said rho G of R is the conditional probability of finding a particle at position R, given that another particle is at position 0. And then we talked about the potential of mean force. We said that the average force experienced by particle 1 is force comes from gradient of a potential, right? So the potential of mean force is the average value of minus dw of R by dr, where w of R was minus 1 over beta ln g of R, right? These are the concepts and the things that we derived in the last couple of lectures. So already you saw that knowing G of R tells you about some sort of thermodynamic average, which is the average force experienced by, and this is a bit subtle. You're really talking about keeping particle 1 and particle 2 fixed at some distance, and you're talking about the force between them as you average out over everything else in the system. Everything else is averaged out, but particle 1 and 2 are kept where at some particular distance, and you're calculating the force between them. So we will proceed further. Now we are going to talk a bit more about how to get thermodynamics from G of R. And specifically, for today, we will do more thermodynamics from G of R. We will do an example, and we will do some general relations. We are going to focus on pair interactions. So our U of Rn, we are going to assume a specific form that it is only made up of two body interactions. After that, we will switch into StatMech perturbation theory. These are the two things we are going to do today. In next class, which is not on Tuesday, next class is on next Thursday, we will be doing application of StatMech perturbation theory. It's likely I do a makeup class one evening, and I will send details of it. And I will also release the midterm details over the weekend, including what teams you are in. So let's get started with thermodynamic property from G of R. So today we will assume pair interactions. What does that mean? So we have a complicated n-body term, U of Rn, which in general depends on U of R1, R2, Rn, all of these things. And we are going to say, and so this could be a sum of two body, plus three body, plus four body, plus really everything at the same time. If you have a neural network, it could be really, really complicated. But what we are going to say is we are not going to worry about these three body terms and four body terms. We are only going to look at the two body terms. So how do I write down mathematically a potential that is made up of only two body terms? That's going to look like U of Rn is equal to I is equal to 1 to n, J is equal to 1 to n, and some little u, which depends only on Ri minus Rj. If you're only going to look at two body terms, there is no point talking about angles, right? You cannot define an angle with only two body terms. Cecilia is missing. That's what I was thinking. Is this correct, or are we overcounting if we write down our n-body interaction in this form? Every pair ij is getting counted twice, right? So I goes from 1 to n. So I is equal to 1 and j is equal to 5 is counted. But then you're again counting I is equal to 5 and j is equal to 1. And you could imagine some potential which is not symmetric, but I don't know what that quite means. We are talking about radial distances. So we don't want to count for the interaction between, say, Ami and Didi and Ami. It does not make sense. There is interaction between Ami and Didi, and period. That's it. That's what it is. Okay. So what we need to do here is either to divide it by half, or another way to deal with it is to write down something like I is equal to 1 to n, and you run your summation j from values more than I, right? The other problem, that's not the only problem with I is equal to 1, what we wrote in the top equation in this one. The other problem is self-interaction. You will also have interaction between I is equal to 1 and I is equal to 1, which for classical systems is okay, but not quite. That is a problem. I will draw an example of U, but if you have things that blow up at R is equal to 0, that's going to be a problem, right? If the interaction between two things blows up as R tends to 0, then self-interaction is going to be infinite, and that's a problem. So we cannot do that. So really, I is equal to J is a problem, plus double counting is happening, right? So the best way to write it, you cannot just divide by half. You have to write it this way: J more than I, and then you are doing U of Ri minus Rj. So this U, small u, which depends on some small r, which is a distance, is a pair potential. So keep in mind that small r is not a vector. Small r is the modulus of Ri minus Rj. It's a number, it's a scalar. So this is a pair potential. And if we expect pair potentials to look something like they become very high as you bring r to 0, then there is some equilibrium length, and then as you take r to very large values, they again become 0, right? So there is some length, some value of r, which probably corresponds to something like a bond being formed. It does not really have to be chemical bond. It could be, does not have to be covalent bond. It could be ionic bond, anything you have, okay? A most popular form for writing functions that look like this is known as Lennard-Jones potential, which says that U of R is equal to A by R to the power 12 minus B by R to the power 6. So this is known as the 12-6 potential, or Lennard-Jones potential. This is just one model where you would fit A and B, for example, by doing scattering experiments and try to get a sense of what are the values of A and B. So you can look up on Wikipedia. There is motivation for why this 12 and 6 term comes. The interaction between two dipoles, it depends in a particular behavior and things like that, you know. So, and you can plot this and see that, convince yourself that it will look like this. As R tends to 0, it will blow up. As R tends to infinity, it will go to 0. And it has a well-defined minimum. So we will be working with potentials of this form. Furthermore, we are going to assume that any two atoms have the same U of R. We have already assumed that, right? I'm not saying U12 of R, U23 of R, right? It's all the same. If you have two component system, for example, you would have to talk about two types. Well, at least three types of interactions, right? Interaction between A and B, B and B, and A and A, right? So in a one component system, there is only one U. Okay, so what we are interested now is to calculate the average energy in a canonical ensemble, for an interacting system with pair interactions. We are not going to solve this problem for the most generic case. We are just going to assume the potential model we had so far. And let's call this equation for capital U of Rn as equation number 1. So we, under the assumption that we are working with interaction potentials that look like equation number 1, we want to calculate the average value of the internal energy. And this is subtle. Internal energy is not the same as only potential energy. What we wrote down capital U is potential energy. Internal energy also comes from kinetic energy, right? So average value of internal energy is average value of kinetic energy plus average value of potential energy. Average value of kinetic energy is easy. It's n particles in 3 dimensions. What will be the average value of kinetic energy?
3/2 kBT.
3/2 n kBT, right? How? Why?
Gaussians.
Well, first of all, equipartition theorem. That's the easiest answer. Every degree of freedom consumes half kT. But the more rigorous answer is Gaussian. What exactly do you mean by Gaussian?
I meant the thing you had said about the equipartition theorem and how each of those Gaussian distributions.
So yeah, so this brings me to your DIY one for today. There won't be many. There will be one. So to calculate this, and I will give you the sense. So what you want to do is to calculate the average kinetic energy, right? So let me sketch out the proof. What is kinetic energy? Kinetic energy is something by p square over 2m, right? And you want to calculate the average of this thing, average in the canonical ensemble. So you need to take e to the power minus beta energy. This energy, when you're talking only about the average of the momentum, does not depend on the force field, it does not depend on the potential. This will be part of the probability that depends only on the kinetic energy, right? So this is the type of integral you will be doing. So if you do, and keep in mind here that this is a 3n dimensional vector. So once you do this integral, you will actually be able to show that the average value of the kinetic energy is this thing. And you have to divide by the partition function to get it right. Okay, so please do this yourself and convince that the algebra works out. Otherwise, equipartition is always there. Every degree of freedom gives you half kT and things like that. So that's the average kinetic energy. The average potential energy is the average value of U, the many body potential that we are working with. That's what we need to calculate. So here, I'm going to write down the relation first before I prove it. But even before I do that, I want you to guess the answer. I think you can guess the answer if you really understand what's going on so far in this class, in this interacting system business. You should be able to guess the average value of U. Let me give you some hints. Your average value of U, I expect to depend on U of R12 between two particles, the small u, the potential energy form that we are going to take. We are also talking about two body terms only, right? So I'm not going to assume radially symmetric for now. Let's assume it's more than that. So I expect it to depend on ρ2 of R1, R2. It should depend on these two things. It's not going to depend on P2 because the particles are indistinguishable. So it's not going to depend on P2. It will depend on small u, it will depend on rho. Is anyone brave enough, bold enough, stupid enough to, given this information, to guess what will be the average value of u? Go for it.
I want to say that it is an integral from R12 equals 0 to infinity of U of R12 times ρ2 all times e to the minus beta U of R12.
Sometimes the story in life is to quit when you're ahead. You had mostly right until you got to the e to the power minus beta u part. Remember, how do we get ρ2? We get ρ2 from P2.
Oh, right.
And P2 contains e to the power minus beta u. So what he said is actually quite correct. I will simplify it a bit. So I'm going to integrate over, it's a double integral over dr1 and dr2 multiplied by u of r12. So I am going to every position, every possible pair of position, and looking at what would have been the internal energy if I had one atom at R1 and one atom at R2, right? So I do that. But this does not account for the probability of finding two particles at R1 and R2. What is that probability? That probability is ρ2 of R1, and here I wrote R12, that's wrong, it should be R1, R2. That probability is ρ2 of R1, R2. But I double counted. my R1 is going over all possible things. My R2 is going over all possible things. So I'm going to count every coordinate twice. So I need to put a half here. So intuitively, you can see why this might make sense. It's just an average value of the potential energy. And we are going to prove this. But everyone sees why we don't need to multiply it with e to power minus beta u, because e to power minus beta u is contained in rho 2. We got rho 2 from P2, right? And P2 is integral of e to the power minus, P2 is proportional to e to the power minus beta u, okay? And we will show this, we will prove this. Let's call this equation number 2. For spherically symmetric systems, we will find that again, average E, the kinetic energy part is same, 3/2 n kBt. And this part will now become half double integral dr1, dr2. It's spherically symmetric, so we will be able to simplify it, and we will show that this part becomes half rho integral dr 4 pi r square g of r u of r. Okay? These are the two things we are going to show in the next few lines. It's not too hard. So it's the same idea, but you will be using the spherical symmetry and switch from dr1, dr2 to dr12 and then do spherical coordinates and stuff like that. So first, let's try to show equation 2. And it's important that you understand why this intuitively makes sense before we get into the math of it. Okay. I'll pause for a moment.
Is the integral over dr1, dr2, is that a volume integral? Or is it?
It's a 6-dimensional integral.
Okay.
While this one is a 1D integral, it is just a distance. Are you guys glad you're not at Harvard? You've seen the news, right? They might be stopped from taking any foreign students.
Oh.
Complete stop. It's happening. I went and deleted my Twitter and Facebook because I travel a lot and they are asking people to like show their social media. I'm still on a green card. I do not want to get deported.
Is it because what the president of the university said?
I'm not going to say anything. You can read the news, but yeah. Also, my Department of Energy grant is currently, technically speaking, conditionally terminated. So I have a WhatsApp group with my professor friends at Stanford and elsewhere, and they're like, wait, we just got a notice, your grant is terminated. So I asked the Maryland people, like, is my grant terminated? We were like, yeah, we got the email 2 days ago. We have decided to ignore it and not freak you out because there is a lawsuit filed. So there is a restraining order against the government to not take DOE money from us and things. It's pretty crazy times. Okay, but let's get back to science, which is very nice. No, it is. It's awesome. Oh, the other day, a visiting chemistry professor, someone giving a seminar, told me about an essay in 1905. Boltzmann visited Berkeley, and I will post it on Slack. It's quite interesting. It's called something like A European's Visit to El Dorado. He was very happy that his only problem was he could not get any wine or anything like that. So he talks about all the things, his experience over there. It's kind of fun essay to read. Okay, let's get to this proof. So we are interested in calculating the average value of this n body potential energy, right? Our life is a bit simple because we have assumed pair interactions. So let's write it down. This is going to be average value of I is equal to 1 to n, j more than I to n, small u of Ri minus Rj. Okay. If small u is the same for all I and j, then how many entries does this double summation have? Or otherwise, how many entries? If I write the summation as, summation can be written as term 1, term 2, term 3. How many terms does this summation have?
N times n minus one divided by two.
N times n minus 1 divided by 2. Does everyone agree? If it was I is equal to 1 to n and j not equal to I from 1 to n, then it would have been n multiplied by n minus 1. But since you are saying, so it's going to look like an upper triangle or lower triangle, however you want to think of it, right? If these are all the I values, these are all the j values, you're only considering things like this, right? And if the whole square is around n multiplied by n minus 1, you're taking only half of it. So n multiplied by n minus 1 by 2. And these are pair interactions. So on an average, they will have the same value. So instead of writing the summation, this thing can be written as n multiplied by n minus 1 by 2 of u of R12, average value of u of R12. It does not matter which two particles we are thinking about, R12 will do it, right? Because on an average, it will be the same. Okay, very good. Why did we get this? Because this is the number of separate pairs. Okay. Let's go further. Let's write down this expectation value explicitly. So this is n minus 1 divided by 2. What is the average value of anything in a canonical ensemble? Well, in a canonical ensemble, the average value of anything comes from looking at e to the power minus beta u of Rn, looking at all possible locations, divided by e to the power minus beta u of Rn, where now this is capital U. Okay, this is the many body potential. Remember why, and this is sort of subtle if you don't think about it, or if you think about it, this is the true many body potential. The two particles do not exist in isolation with everything else. You have to look at the average of what's going on in everything else. And what is the thing that goes over here? This is U of R12. So that's the average we need to calculate. Okay. Again, this proof will also look like we are going in the opposite direction, making things more and more complicated until everything falls out nicely. Okay, so what we are going to do now is to keep the half outside and take the n and n minus 1 inside. The denominator, we are not going to do much. The denominator, we will keep drn e to the power minus beta u of Rn. In the numerator, we will split things out. So in the numerator, this drn is dr1, dr2, dr3, dr4. It's all the r's, right? So let's write it down like this. First, let's write down dr1. Then let's write down dr2. Then we write down u of R12. Why did we do it this way? Because small u does not depend on R3, R4, R5, right? So let's separate out the variables that small u depends on, and let's do the other variables separately. Then we put in the n of n multiplied by n minus 1 over here. You will see in a moment why we do this strange looking thing. And here we are going to have d of r n minus 2 in the superscript, which means that this thing is dr3, dr4, drn, everything except r1 and r2, multiplied by e to the power minus beta u of rn. Okay. So pay attention to this part in blue. This part in blue turns out to be related to something simpler, and we can express this in terms of our rho 2. What's the connection of this with rho 2? Well, what was rho 2? Recall, and let's call this equation 3. So recall that rho 2 of R1, R2. What was the definition of rho 2 of R1, R2? Actually, my blue is a bit wrong. What I am going to do is to also include the n minus 1 in this blue. That will also go inside. What was the definition of rho 2 R1 R2? It was n multiplied by n minus 1 multiplied by P2 of R1 R2, right? That's how we defined it. What is P2 of R1 R2? Well, that's the thing we wrote down there. So this whole thing is rho 2 of R1 R2. So if you remember n of n minus 1, what is P2? P2 is integral of dr3, dr4, drn e to the power minus beta capital U of Rn divided by the full partition function drn e to the power minus beta U of Rn. So if you notice, the thing in blue is exactly rho 2 of R1 comma R2. It just popped out right there. So we can certainly simplify equation 3. Equation 3 thus becomes average of U of Rn is half integral dr1 integral dr2 small u of r12 multiplied by rho 2 of r1 comma r2. Let's call this rho 2 equation as 4 and let's call this one as 5. This is what we set out to prove for the non-spherically symmetric case, right? The average value of u is, so you can see rho 2 is a probability in this mixed, is in this ensemble where everything is interacting. It tells you the probability of finding two things because it averages out everything else. I'll pause for a moment. Any questions about this? No questions? Okay. So we got, so this was, where did it go? Equation 2, right? That the average kinetic energy is this thing. So let's go from here. Equation 5 was, oh, sorry, is equation 2. Okay. So now we will say, we will study what happens to equation 5 if we had spherically symmetric molecules. In that case, rho 2 of R1 comma R2 becomes rho square of G of R, right? This is how we defined our G of R, the radial distribution function. Furthermore, rho 1 of R1 is equal to rho for spherically symmetric molecules, irrespective of whether we have interactions or not. So let's use equation 6. Use equation 6 in 5, which is the same as 2. What do we get? We get U of Rn, the average value of the n-body interaction, which we just wrote as half dr1. And to be careful, I will write down a vector now because soon we have to get rid of the spherically phi inside type things. dr1, small u of r12, rho 2 of r1, comma r2. Okay, this can be written in the following form. So here, what are we doing? We have a vector, we have two vectors, right? So do I have another pencil? I don't have a pencil, but anyway, you can use. So this vector is the iPad pencil is going over all R1, and this, my finger is going over all R2, right? And they are going all separately. You can do one more thing. You can make this one go all R1, and Julia, you're on Zoom, so you cannot see my Apple finger moving vigorously. So this is going over all R1, and instead of thinking about this going over R2, we think of the difference from here to here, right? So you look at R1 and you look at R2 minus R1. It's the same thing. So we will have half dr1, and now we will talk about dr12, and then we will have U of R12 rho 2 of R1 comma R2, but we are talking about spherically symmetric things. So if you're talking about spherically symmetric thing, this integral can be carried out. dr12 is going to depend only on the distance r12. The phi and psi term between the tip of the first vector and the beginning of the other vector, that's not going to matter. So this will become half integral dr1 integral scalar dr12, I have removed the vector now, multiplied by u of r12 multiplied by 4 pi r12 square g of r12. Now notice that this is r12 is just a variable here. There is no point in calling it r12. We can call it dr. It's the same thing. It's an integral variable, right? So this thing becomes half integral dr1 integral dr small u of r 4 pi r square g of r. Furthermore, this thing in the red and this thing in the blue are two separate integrals that are product of each other. What is the value of integral dr1? V, it's the volume, right? It has to go everywhere. So this thing now becomes half V. Oh, you saw Pakoda yesterday, right? Didn't I cross you on the trolley trail in the evening?
Yeah,
You saw Pakoda. Yeah, good thing you didn't try to say hello to him. He would have tried to bite you. He's a bastard. I get worried sometimes students see him. There's a guy, Kinjal, he's very sweet in biophysics in third or fourth. Every time he sees Pakoda, he tries to like give him a hug. And Pakoda is like, get out of here. Why are you coming to me? Now he has learned the hard way. dr u of r I missed something. I missed my rho square, right? Density squared. UR. Actually, let me. Yeah, that rho square is correct. What I want to do is to write this integral slightly differently. So dr 4 pi r square rho square g of r u of r. Okay. Just being consistent with my note. So this rho square, I'm going to bring outside over here. It does not depend on r, it's an independent. So I get capital U of Rn averaged is half rho square V integral dr 4 pi r square g of r u of r. Okay, I'll write down the last equation on the next page. So this thing is half rho square V integral dr 4 pi r square g of r u of r, which is the equation, last line on this page. Okay, what is the value of rho multiplied by V? What is rho? Rho is n divided by V. So rho multiplied by V is n. So rho square V is equal to nV. Rho is equal to n by V. So rho square V is equal to rho multiplied by rho V is equal to rho n. Okay. So now I can write down my full energy, which is the sum of kinetic energy that you're going to do at home today or tomorrow, 3/2 n kBT plus half multiplied by n rho, this thing, multiplied by dr 4 pi r square g of r u of r. So if I'm interested, energy is an extensive quantity, right? So why dangle the n both sides? If I'm interested in energy per atom or per molecule, whatever you're, in this case, it's per atom that you're looking at, that will be average value of E by N is equal to 3/2 kT plus half rho integral dr 4 pi r square g of r u of r. This is the relation that I wanted to show. If you know G of R, so let's take a slightly big picture look here. Why was it so hard to calculate the average energy per atom? The average kinetic energy was easy. If you had an ideal system where nothing interacted with nothing, anything interacted with nothing interacted with anything else. Now, what am I saying? You know what I mean. There is no interaction between any two particles, right? In that case, the average potential energy is zero. We did phonons and electrons and things like that, right? There we said, well, they experience a potential energy, but they are not interacting with each other, right? So we just did the potential energy for one particle, which whether it's in ground state or excited state, and multiplied it by n. Now we have something messy. Now we have two particles that talk to each other, but at the same time, this particle talks to this one, and this particle talks to this one, and this particle talks to this one. It's a complex network. Even though it's a complicated interaction, it's a network. So you cannot just look. So so the thing is, even if you knew U of R, what is the potential energy between two particles, that is not the same as asking what is the average potential energy of the system. Because average, you could not have just done, well, I know U of R, so all I will do is to do something like U of R e to the power minus beta U of R, and that will give me my average potential energy. That's not going to work. Why? Because this excludes what is everything else doing, right? So this is, imagine all of us are connected with springs, harmonic springs. It's going to be really funky, right? If you pull me over here, and Didi is, let's say I'm connected to all of you. Let's simplify it even further. Let's say I'm just connected to Didi with a spring. Didi is connected to Louis with a spring. Louis is connected to Noah with a spring, so on and so forth. Even here, if you pull me over here, Fatemeh will feel the effect, right? And if you want to calculate the average energy between Didi and me, you have to account for whatever complicated dance Fatemeh is going to do because of us getting pulled. And that's why it's so complicated. In other words, you have to account for the entropy of the system. And that's hard, right? So that's why we got such a complicated term. And I did not derive anything for this. I could write down such a mathematical thing only for assuming a two-body potential. If I did not have a two-body potential, I would not be able to write down something like this. People have done in the 70s, when computers were very, very clunky, people used to do a lot of algebra. And they have there, if you read Macquarie, there are expressions, second order expressions for what happens if you have more than two body terms, and people used to write papers and things like this, right? And they would use it to actually go do spectroscopy and things like that, calculate G of R, and infer the nature of matter, nature of chemicals and things like that. Any questions about this? Okay. So before I get into perturbation theory, I want to take a slight pause and think very big picture about what the connection between G of R and the potential energy of the system. And I will tell you about a very interesting theorem known as Henderson theorem. On Slack, I will post the full proof of this Henderson theorem. It's a one-page proof. I actually timed it, so it should be in your Slack in like 7 minutes from now. So my question is as follows. Well, before I get to my question, let me remind you of how G of R looks like, right? So we plotted G of R for an ideal gas. G of R looks like a straight line, which is equal to 1, right? For a liquid, it's going to have some peaks that looks like this. Liquids are not entirely structureless, right? Liquids do have some structure. In fact, water has quite well-defined structure locally. For any material, it will, at very long distance, it will go to 1. Does not matter what is the nature of interaction. If you go really, really far, everything approaches 1. For a crystal, these peaks will be sharper, and it doesn't have to be exactly at the same distance as the liquid, some things like that. So this was our G of R. And my point to you was that G of R can be obtained from an inverse Fourier transform of S of K. S of K is what you measure in scattering experiments. So here's my question. if I told you the full n-body potential, if I gave you the exact algebra for what it is, so it's a complicated function, right? But it's just a number, right? What is U of Rn? U of Rn is, you tell me the vector corresponding to R1, R2, R3. It's a computer program that will then tell you one number, the potential energy of the system, right? And this could be as complicated as you want. Again, it could be a deep neural network. We don't care. Given U of Rn, can you have only one G of R, or will there be multiple possible G of Rs? Given this, is G of R unique? Think. Max, what do you think? Why?
Because there are pair interactions.
He's using words, which might or might not be sensible. I cannot tell. I will give you the benefit of doubt. Nah, I won't.
If I have say a constant potential in substrate.
Yeah.
For which I have particles.
Yeah.
Since I go back and forth with derivatives, that constant potential might shift the landscape of the energy. So up to a constant potential, I don't think GR will be unique. But the peaks should stay the same in the case if it's a crystal. But if there's a constant gradient in a liquid, then that might shift the peaks a little bit.
But the potential is same. For the same potential, can you get two different G of Rs or not, is my question, at the same temperature? I'm looking for more volunteers. Go ahead.
I wanna say that it's unique because if it weren't, I feel like that it reminds me of how like in thermodynamics, there can only be like one set of macroscopic variables that maximizes the entropy for some given conditions. So if there was more than one G of R, then that feels like it would inherently not be a thermodynamically stable.
That's not a wrong answer, but the answer is simpler, and I'm still fishing for it. Anyone? My hint to you is think about the formula that we use to calculate G of R. Where does G of R come from? It comes from P2, right? G of R, I mean, spherically symmetric, whatever, but in the end, what you really, where does G of R come from? G of R comes from the difference between P2 and ρ2, right? And what is P2? P2 of R1 comma R2 is proportional to dr3, dr4, drn e to the power minus beta u of Rn. If you know e to the power minus beta u of Rn, you know P2 of R1, R2. If you know P2 of R1, R2, you know G. There is no difference. So if you know U of Rn, for construction, G has to be unique. I'm not saying it's position independent. Those are some very complicated, funky looking thing. But you can't have two different G of Rs. Okay? If you go from a fixed potential, you will get the same G of R. Potential energy has way more information than G of R. G of R is effectively accounting for behaviors of the potential energy. So hopefully this makes sense. Now let's go even crazier. If you knew G of R, if you were able to calculate some value of G of R, is U of Rn unique?
But you just spoiled us the answer because you said that it contains less information.
So it should not be, right? You should get the same G of R. You cannot really tell what is the n-body complicated interaction, right? Maybe there's some cancellation of error going on, right? Everyone sees this? So this is true. Given a U of Rn, G of R is explicit. But you can see G of Rn is this integral. So it's like to say that in the general case, you could go from G of R to U of Rn would be the same as saying if you tell me the value of a 6-dimensional integral, I can tell you what was the function you were integrating. No, you can't do that, right? It's not going to work out, right? There's some other function. This is not going to work. However, there is a very interesting but utterly useless theorem, which happens with a lot of things that are very beautiful. They are utterly useless. So you cannot, when I first read it, I got very, very excited. And again, I went to my colleague, John Weeks, who was a postdoc when this theorem was discovered in the early 70s. And he was like, oh, that is the most useless theorem ever, blah, blah, blah. He went ranting for 1 hour. I mean, but the theorem is quite striking. This theorem is known as Henderson theorem. And I think there's a reason why John Weeks got so upset. So John Weeks and David Chandler, who's the author of your textbook, and Hans Anderson, who was a professor at Stanford, they did a very famous theory called Weeks-Chandler-Anderson that you'll read about in the second midterm. And they were all postdocs then. And this paper took 2 years to get accepted. And one of the reviewers was very, very mean. It went through like 3 or 4 rounds of reviewing. And John suspects Henderson was the reviewer. So he still harbors ill will against him. But that's dangerous. You should never guess who your reviewer is. You know, I have done this mistake a few times. So Henderson theorem says, yes, sure, you cannot go from G of R to a unique U of Rn. But for a system with only pair interactions, G of R uniquely determines U of R up to an additive constant. And we don't care about additive constant, right? That's just shifting the scale. Up to an additive constant. This is amazing if you think about it. The first time I thought, like, wow, this is crazy. This just changes my life. I really felt that way. Like, wow, this is like, I've learned the most, like the first time you read about special relativity, or I don't know. There are things in science that invoke that feeling, right? Like you feel suddenly that you have figured out something incredible. This is how I felt about this one. And the proof, it will be on Slack. It's a 1-page proof. It's really simple. It uses something known as Gibbs-Bogoliubov inequality and works through it, and it works out quite nicely. The proof is also connected to, so Gibbs-Bogoliubov inequality is connected to the topic we are going to do next, which is Zwanzig's perturbation theory. So go through that proof. Even though this Henderson's theorem is not in your exam or anything, I do suggest that you go through it. It's already on the website, and actually, maybe I can open up the proof. 687. No, I don't want dermatologist. Where is it? Somewhere. Yeah, it's a 1-page proof by Marcus Di Sarno at Carnegie Mellon. He used to be at Max Planck in Mainz. He was a group leader there back in the day. So in 1974, R.L. Henderson proved that for classical or quantum fluids with only pairwise interaction, the pair potential U of R, which gives rise to a given radial distribution function G of R, is unique up to a constant. It's kind of amazing. And it uses this Gibbs-Bogoliubov inequality. Some people also call it the Feynman-Gibbs-Bogoliubov inequality. It is related to, if you have, we will be doing Ising model later, and this is how we solve Ising model. It's also related to mean field theory and things like that. And so I recommend working through it. The proof is quite elegant. So the reason why John Weeks said this is utterly useless is because nothing is only pair body interaction, right? So you can't do anything with it. There is always other interactions that happen, right? So you think this is nice, but it does not help you at all. Reality always have pair body interaction. And secondly, it shows you that given G of R, U of R is unique, but it does not give you a pathway of how to find it, right? So it's sort of like a mathematician's proof. It says that, yes, it exists, but I'm not going to tell you how to do it, right? So, but people still try to use it to do things, you know, it's cute and sort of profound, but it's, and this 1-page paper, which is on the class web page on Slack, is worth reading, especially the proof of this Gibbs inequality. That's itself an if we have time later, we will talk a little bit about machine learning. So when people train deep neural network models, they use something known as variational inference, which is basically this Gibbs inequality. Or all it does is to use something known as KL divergence between two distances is always positive, which is what you're seeing in equation number 5 over here. If these last few words did not make sense, don't worry about it. Let's get back to StatMech. So this is Henderson theorem. It's interesting. Read up the proof. I'm not going to ask you anything about it ever, but it's interesting. And it's kind of amazing that it shows you, while it's obvious that from U of Rn, G of R is unique. Of course, for the same G of R, there can be many different n-body potentials, but if you're willing to assume that it's only pair interactions, it's unique up to an additive constant. So it's kind of amazing. It's a bit like quasi-crystals. They've got the Nobel Prize. Is there anyone here who does not know what's quasi-crystal? Raise your hand, don't be shy. Tisha does not. You're an undergrad. She's going to Chicago, by the way. I did not turn her off from StatMech. So that's cool. She's going to do a lot of StatMech in Chicago. So quasi-crystals are things which have 5-fold symmetry, and Linus Pauling proved that in real crystals, you should only have 2-fold, 3-fold, 4-fold, 6-fold symmetry. That's it. And then in 1984, Daniel Shetman discovered these X-ray diffraction profiles, which have 5-fold symmetry, 7-fold symmetry, 11-fold symmetry. Went crazy. And turns out in my undergraduate student in India, my professors had discovered that in 1976. And they thought this has to be wrong. So they just published it in some arcane Indian journal. And they used to show me their X-ray diffraction profile from mid-70s where they had this symmetry. And it blew everyone's mind away. And Linus Pauling, who got 2 Nobel Prizes, insisted that it is wrong till his deathbed. He insisted this is diffraction of a diffraction. And he insisted so hard that people had to believe him because it's Linus Pauling, right? So Shetman finally got the Nobel Prize a few years after Linus Pauling died. And no one has found any use for quasi-crystals. Some people tried to use it in frying pans. Apparently, it has very low coefficient of friction, but it's a very expensive frying pan. You cannot do anything with, right? So this Henderson theorem is kind of like a quasi-crystal. It's not very useful, but it's super elegant that something like this exists. So I can call it here quasi-crystal of StatMech. Maybe one of you will find some use for it. Okay, so now we are going to switch gears slightly. Well, not really. We will still talk about interacting systems, but we are going to talk about looking at interacting systems in a perturbative manner. Right now, we looked at the full U of Rn. Yes, we came down to 2-body potentials, but we assumed it's a full-on interaction. We are not going to assume anything about it. StatMech perturbation theory develops a way to turn on these interactions in a perturbative manner. And today's remaining class and the next class on Thursday, we will see how it's put to use. And in your second midterm, you will look at one of the papers will be free energy perturbation, which really puts it to use for modern day drug discovery and a variety of things. In fact, DeepMind people 2 years ago wrote a paper. Let me tell you a little bit about the history of this. So, and before I get to DeepMind. So Zwanzig did this in 1954. Feynman also has a paper on this, and I'll put this all on Slack from around 1954, similar ideas. Feynman's paper is called Polarons in slow-moving crystals or something like that. And Zwanzig had 5-part papers where he worked on all this. And people have continued to work on this. And in 2022, there is a DeepMind paper on this where they try to use machine learning networks to really do Zwanzig's formula in an automated manner. That paper I particularly point out because the first author on that paper is Andy Ballard, who used to be a PhD student here in our IPST building. And then he went to work at DeepMind. So that's a StatMech connection, IPST connection. But we will talk about the Zwanzig formulation. So idea is quite simple. We have a n-body complicated potential, right? Super messy. Everything is talking to everything at the same time. Let's call this as the true potential. Let's say that we can write down this potential as a sum of So I will use the symbol here where I call U of Rn as U subscript n, okay? And also, I don't think, so the fluids part, the part that I did so far, the G of R and everything, that was Chandler chapter number 7. This is not in Chandler. This is in Macquarie's book. There are enough PDFs floating around online, even if you don't have a copy. Macquarie's book, chapter 14, talks about Zwanzig's perturbation theory and other things. So this U of n is the true potential, which is very, very complicated. Let's write it as a sum of two things. Let's say this is the sum of a reference potential, UN0, which we call our reference potential, plus some deviation from the reference potential, which we call our perturbation, plus UN1, which is my perturbation. So what do I mean by this? So if I think about a system where I have harmonic interactions, right? So this is my true potential. I could split this as a sum of a reference potential, which is an ideal gas, plus a perturbation, which is the spring interaction, right? This is not going to be very useful because your spring interaction, your perturbation is the same as your true potential, right? It might look like, what am I going to do with this? It turns out it's quite powerful. And Zwanzig's formula will show you why it is quite powerful. Okay, so this is our hierarchy. What we want to do, what we really want to do is to calculate thermodynamic averages using this true potential, right? So our main object of interest is to take some observable O, right? It could be heat capacity, it could be thermal expansion coefficient. How do we calculate this observable O? We are interested in calculating this observable O by going to all atomic positions, looking at the value of this observable for those atomic positions, and I'm ignoring the momentum part, okay? Looking at this complicated potential e to the power minus beta u of Rn, and then doing the Rn e to the power minus beta u of Rn, right? But this is a mess because e to the power minus beta of u of Rn depends on everything at the same time, right? So this integral cannot be split into a product of simpler integrals. It's a complex, super, super horrible integral. Like I have been doing so far, I am going to write down the answer of Zwanzig's, the final relation that we are going to prove, to give you why I think it is so profound. Before I get into the proof of it, okay? Zwanzig says that the reference partition function for the true potential, and why do we care about the partition function? Well, of course we do. If you know the partition function, we can differentiate it, we can log it, we can do whatever we want, and we can get everything out of it, right? So we will show that the reference n-body partition function, what would be the relation between Zn and the, sorry, this is the true n-body partition function. And let's think, how is it going to be related to the reference n-body partition function, right? Where there is the reference potential. Let's call this Zn0. What would be the relation between these two? If the perturbation, if this thing was 0, equal. Everyone sees that, right? It will be equal. But of course, the perturbation is non-zero. There is some complication. So that's what we need to calculate, right? And we will show that this perturbation is the same as calculating the average value of the exponential of the perturbation, UN1, but we will carry out this ensemble average in the reference potential. And this is what makes this formula so powerful, because this subscript 0 over here means that you are not going to simulate the complicated system with all interactions. If your reference potential is a hard sphere, you will simulate the hard sphere and just calculate e to the power minus beta UN1 in that hard sphere. You can immediately see why this is elegant, hopefully, but you can also see why this is probably kind of useless if we are not careful. Anyone sees why it might be useless? If the perturbation is very large, if the difference between the true potential and the reference potential is very high, if un is very, very large number, what will be the value of e to the power minus beta un? It will be an extremely small number, right? And try doing math on extremely small numbers. MATLAB stops at 1e minus 18. In fact, if you use MATLAB and try to do 1 divided by 3 plus 2 divided by 3 minus 4 divided by 5 minus 1 divided by 5, which is 0. Every once in a while, you will get the answer 1e minus 18. It's the computer 0, right? So if the perturbation is very, very large, you cannot exponentiate very, very large things with a plus sign or a minus sign. If you do it with a plus sign, of course, it will blow up. If you do with a minus sign, you will get errors, right? So that is the challenge in practice. But people have a workaround of it. And in fact, I will show you late in next class that how we can use this to calculate Van der Waals equation of state by working in ideal gas. So this is Zwanzig's relation, which we are going to prove next. We'll work through the proof. It's not super complicated. I'm going to show you one thing because Zwanzig was, of course, he's like, let's see if I can find the photo. He was at IPST for so like more than 2 decades. No, I don't need this one. This is not the Zwanzig I was looking for. 1 second. Zwanzig. I want to show you a photo. Let's see if you all. Sometimes I go on tangents because I also feel like I have covered too much material, and if I go too fast, you are all going to suffer. I will have to. Did I find it? No, the thing I'm looking for, I cannot. I'm not a robot. Okay, this does not want me to show it to you. I will post it later. So in chemistry, one of the nice things is when you turn 65 and you're still in the game and you're still surviving. And if you're famous, then people do like a birthday party for you. And it comes from the old German word, and they do a special issue in Journal of Physical Chemistry. It's known as Festschrift, which is a celebration. And then people write articles. They don't write about you, but they write articles, and you get to write your autobiography. So Zwanzig has his autobiography there, which is very, very interesting. And in that photo, he's basically sitting in the IPST 1116 room in the corner of it with his feet up on the table like this. You know, it's a great photo. But I will put that article later. Let's come back to this one. And in general, Zwanzig's articles are wonderful. They are worth reading. They are underappreciated. He also has a book on non-equilibrium statistical mechanics, which is full of typos. Okay. So this is the relation. The relation between two partition functions can be calculated out by doing an ensemble average in this simpler partition function. If this ensemble average was in the true partition function, we would be hopeless. Nothing would work out. So let's prove this. So we will start with our true n-body partition function in the true potential. What is this? This is e to the power minus beta un, which is my true potential, dr1, dr2, drn. Okay, but remember our reference, our true potential is un0, the reference potential, plus un1, the perturbation, right? So this is true, this is reference, and this is perturbation. So this integral can be written as integral e to the power minus beta un0 multiplied by e to the power minus beta un1 multiplied by dr1, dr2, drn. Now I'm going to do something which is multiply and divide by the same thing, which is a trick which works in StatMech quite a lot. Of course, you need to know what is that same thing that you need to multiply and divide by. In this case, that thing will be e to the power minus beta un0 dr1 drn integral e to the power minus beta un0 dr1 drn. Does this thing have a name? This is Zn0. This is the partition function in the reference potential, right? While this one is the partition function, true partition function, and this is the reference partition function. So if it was an ideal gas, this is an easy partition function, right? Everything is independent. So this is a partition function. We want to be able to calculate easy. So we have just multiplied, divided by that partition function. Okay, now we are going to do something even more interesting. What we are going to do is to take this Zn0 and bring it up here, okay? So we will write this down as Zn0 multiplied by integral of e to the power minus beta un1. Notice that I switched the order. We are not in quantum mechanics. Product of two things is the same as AB is the same as BA. If you were in quantum mechanics, we'd be screwed. We'd have to do Trotter formalism and things like that. But in this course, h bar is equal to 0. Well, except when it is not.
I feel like one would maybe be a better argument. Zero.
There is a joke about this. So this Festschrift that I was pointing out. So Zwanzig's did not have an autobiography. He had a biography written by someone named Dave Thirumalai, who was a professor here. I got my position because Dave Thirumalai left for UT Austin. Dave Thirumalai's autobiography talks about Michael Fisher, and when Dave Thirumalai joined IPST as a young assistant professor, and Michael Fisher took him out to lunch to one of the restaurants where Taqueria Habanero used to be, and asked, what are you going to do? He said, I'm going to do quantum mechanics. And Michael Fisher told him, in IPST, Planck's constant goes to 0. That's what came to my mind. I'll post that article also. I like the history of science. It's fun. So un0, dr1, drn. Okay, so in the top, it's the same thing. I have kept the Zn0 as is in the bottom, and in the top, I've switched the order. Notice this thing. If this was some function, forget for a moment that it is e to the power minus beta un1. If this was some function, what is this thing in the bigger red circle doing? It is calculating the ensemble average of that function in the reference potential. This is e to the power minus beta un0 on both sides, right? Bingo, we have proven Zwanzig's formula in 2 lines, which is incredible. So we have just shown that Zn is equal to Zn0 multiplied by the ensemble average of e to the power minus beta un1, the perturbation in the potential energy in the reference potential. That's it. This is Zwanzig's formula we just proved, and this is exact. This is not assuming any pair interaction terms or anything like that. This is an exact term. So, of course, like I said, in practice, if your perturbation is too large in the reference potential, if you try to do reference potential as hard sphere, and your true system is some organic semiconductor with electrons talking to phonons and all kind of funky stuff, this equation won't work because UN will be so large. It will be very, very messy. So the trick to, of course, work with this is to turn on the perturbations gradually, right? So I will not really use this turning on perturbations gradually thing in this class. I will just write down the formula. In next class, what we are going to do is to work with only one perturbation, and that will be enough for us. But in the paper that I give you, you might see something related to this. So I will just write this as, you can show that if your true body potential, UN, your true potential can be written as some reference, which is now hard sphere, very easy, no interaction, plus a little bit of perturbation, plus another little bit of perturbation, plus another little bit of perturbation, right? So you're adding, you're gradually turning on the bonds. And you have a hierarchy like this. Then you can show that Zn will be given by, again, Zn0, the partition function in the reference potential, multiplied by e to the power minus beta un1 calculated in 0. multiplied by e to the power minus beta UN2 calculated in one. And now this actually becomes useful because you're doing it step by step, and you can use parallel computing here. You can split this into different computers. One computer takes care of this, one computer takes care of that, and things like that. And it suddenly becomes super useful. So I thought this is quite cool. Any questions about this? So next time, let me draw out from here what material do we have left in this course, okay? So you can read up on it. So next time, so going forward, and no class on Tuesday, next class is on Thursday, we will do application of Zwanzig's formula. That will finish our third part of the course, which is interacting system. Then we will move to the fourth part, where we will look at phase transitions. And to look at phase transitions, I will introduce you all to a very popular model known as Ising model. Ising model was given to Onsager by his PhD advisor to keep him from distracting him in the 1940s. He thought he will keep him busy because there is no solution. But turns out Onsager solved it and got the Nobel Prize for it. And we will study that. It has phase transitions. I will show you how a 1D material cannot have phase transitions. You need to have at least 2D to get phase transitions. We will study Ising model through three different things. We will use an intuitive idea, which is known as PEIERLS, Pearl's droplet argument, which is kind of nice. Then I will introduce you to mean field theory, which is approximate but works well, especially as you go to many, many high dimensions. And then I will talk about broken symmetry and correlations in the Ising model. So Ising model will be our launching point to talk about some very complicated ideas that you will see later in your research again and again and again. And finally, I will show you something known as, over half a class or one class, I will show you something known as renormalization group theory. So while Onsager won the Nobel Prize for Ising model in the 50s or 60s, renormalization group theory led to another Nobel Prize to Ken Wilson in 1970s. And that might be the last topic. I might do a little bit of connections to, I'll see if I have time left, either I will talk a little bit about machine learning, or I'll talk about how to get kinetics from StatMech if I have time. But if you can cover all this, I would say it's been a fantastic semester. You guys have covered a lot of things. So we'll work on this, and I will do one makeup class in the evening in IPST. Those of you who cannot join can join on Zoom. If you can join, I will provide pizza. Okay, and I will take a poll of all of you to maximize that people can join in person. And I will release second midterm details over the weekend. Any questions? Okay, see you on Thursday.